Embedding in concrete with crushed stone 0 in a 1:3:4 mix ratio or mortar, in a 1:3 mix ratio. Embedding materials in concrete or mortar ensures durability, stability, and structural integrity in construction. When using concrete with crushed stone 0, a 1:3:4 mix ratio is commonly applied. This means 1 part cement, 3 parts sand, and 4 parts crushed stone 0, fine aggregate with minimal coarse particles. This mix provides a strong, compact, and uniform structure suitable for embedding pipes, structural elements, or other components requiring solid support. The inclusion of crushed stone 0 instead of traditional gravel results in a smoother mix, reducing voids and enhancing adhesion. For embedding in mortar, a 1:3 mix ratio is used, which consists of 1 part cement and 3 parts coarse sand. This mortar mix is suitable for binding, coating, or embedding smaller elements where high compressive strength is less critical than flexibility and adhesion. It is often used for plastering, masonry, and ceiling joints. The coarse sand in the mix provides a rough texture, enhancing mechanical bonding and preventing cracking due to shrinkage. During the embedding process, the material should be evenly spread around the embedded object to ensure full coverage and maximum strength. Spreading mortar with a 1:3 mix ratio, 1 part cement, 3 parts coarse sand, ensures strong adhesion and durability. It is applied evenly, compacted, and leveled for masonry, plastering, or embedding materials. Proper curing enhances strength. Drill a 6 cm diameter hole precisely to accommodate the pump, ensuring proper alignment, stability, and secure installation within the structure. The cover, 55 mm thick, will be constructed from galvanized or zinc-plated sheet metal. For corrosion resistance and durability, it will be securely embedded in the slab to ensure stability and longevity. The semi-buried cistern requires a minimum diameter of 4.4 meters and a 1.08 meter deep circular excavation for proper structural stability and capacity. To begin the construction of the cistern, a circular circumference must be accurately marked on the ground with a diameter of 3.5 meters. This marking serves as a guideline for excavation, ensuring proper alignment and dimensions for the foundation. The excavation depth should be between 20 and 30 centimeters, providing a stable base for the structure. The soil must be evenly removed and leveled, avoiding irregularities that could affect the cistern's stability. Once excavated, the base should be moistened and compacted to enhance its load-bearing capacity. This preparation ensures a solid foundation for the subsequent construction phases of the cistern. Marking the circumference with a radius of 1 meter and 54 centimeters, 1.54 meters, is a critical step in ensuring the correct dimensions for the cistern's foundation and walls. The radius measurement is taken from the central point of the excavation site and extended outward to form a precise circular boundary. This results in a total diameter of 3.08 meters, which defines the base of the structure. To achieve accuracy, a stake or marker should be placed at the center of the intended cistern location. A string or measuring tape of exactly 1.54 meters in length can be attached to the marker and used to draw the circumference by rotating it 360 degrees, ensuring a consistent circular shape. It is essential that the marking is clear and visible to guide the excavation process effectively. Once the circumference is marked, excavation should begin carefully, following the marked boundary to maintain uniform depth and shape. Any deviation can affect the stability and alignment of the cistern walls. The excavated soil should be removed evenly, and the base should be leveled and compacted to prevent future structural issues. By adhering to the 1.54 meter radius, the cistern's construction will have the proper dimensions to support the required water capacity. This careful preparation ensures that the walls, foundation, and overall structure remain stable, durable, and functional for long-term rainwater collection and storage. The cistern walls will be constructed in 5 continuous layers, ensuring structural integrity and uniform strength. Each layer must be applied without interruption to prevent weak joints or cracks. The wall thickness will range between 1 to 1.5 centimeters, providing a balance between durability and flexibility. A 1 to 3 mortar mix will be used, consisting of 1 can of cement and 3 cans of medium sieved coarse sand. This composition ensures optimal adhesion, water resistance, and strength, crucial for maintaining the cistern's longevity and preventing leaks. The cistern walls will be constructed in 5 successive layers, ensuring strength, durability, and uniformity. Each layer must be applied continuously, without interruption, to prevent weak spots or separation between layers. The thickness of each layer will range between 1 to 1.5 centimeters, ensuring structural integrity while maintaining flexibility to prevent cracks. A 1 to 3 mortar mix will be used, consisting of 1 can of cement mixed with 3 cans of medium sieved coarse sand. This ensures optimal bonding, water resistance, and durability. Proper curing is essential, so each layer must be kept moist to enhance strength and prevent shrinkage cracks. Before applying the first internal layer, it is crucial to wait at least 12 hours after the external layer has been completed. This waiting period allows the external layer to partially cure, ensuring it has enough strength to support the internal application without deforming or cracking. During this time, the external layer should be kept moist to prevent premature drying. Once the 12-hour period has passed, the first internal layer can be carefully applied, ensuring even coverage and a smooth, uniform finish for proper adhesion and durability. The second internal layer must be applied following the same procedure as the first internal layer to ensure uniform strength and adhesion. A minimum waiting period of 12 hours after the first internal layer is required. Before application, the surface should be moistened to enhance bonding. The mortar must be spread evenly, ensuring a smooth and durable finish. To eliminate sharp corners inside the cistern and improve its structural integrity, a 10 cm thick layer of mortar should be applied in a half-moon shape where the floor meets the walls. This rounded transition, also known as a fillet or cove, prevents stress concentration, reduces the likelihood of cracks, and enhances water resistance by eliminating hard angles where debris or water pressure might cause weaknesses over time. Before applying the mortar, ensure the floor and lower wall sections are clean and free of debris, dust, or loose particles. Moisten the surface slightly to improve adhesion and prevent rapid drying, which can lead to cracks. Use a 1 to 3 mortar mix ratio, 1 part cement to 3 parts coarse sand. Add water gradually, mixing until the mortar reaches a workable, smooth consistency that is easy to shape but not too wet. Application of the half-moon shape. Using a trowel, apply the mortar along the junction of the floor and wall, ensuring a consistent 10 cm thickness. Shape the mortar into a smooth curved transition, resembling a half-moon. This can be done using a rounded tool or by hand while maintaining even coverage. Curing and finishing. Allow the mortar to set gradually, keeping it moist for at least 7 days to prevent shrinkage cracks. Regularly check for uneven sections, smoothing them out for a seamless transition. This rounded edge improves the cistern's structural strength, facilitates easier cleaning, and ensures long-term durability by preventing weak points where water pressure or settling might cause damage. The Urucu-Coari-Manaus gas pipeline is one of Brazil's most ambitious energy infrastructure projects. Designed to transport natural gas from the Urucu oil and gas fields in the Amazon rainforest to the state capital, Manaus, constructed by the Andrade Gutierrez engineering group in partnership with other companies, this 670 kilometers pipeline traverses rivers, wetlands, and dense forest, presenting extreme logistical and environmental challenges. The project was not only a feat of engineering but also a testament to innovation, sustainability, and social responsibility in one of the world's most ecologically sensitive regions. The Amazon rainforest, home to immense biodiversity, is also rich in natural resources, including petroleum and natural gas. The Urucu-Coari-Manaus pipeline was built to harness these resources efficiently, reducing dependence on diesel fuel and lowering greenhouse gas emissions in the region. The gas transported through the pipeline supports the energy needs of Manaus, Brazil's second-largest industrial hub, as well as several smaller municipalities along the route. The project was undertaken by the Amazonas Gas Consortium, which included Andrade, Gutierrez, and Carioca-Engenharia. Their main challenge was to construct a pipeline in a region where conventional methods were often impractical due to difficult terrain, unpredictable river levels, and the need to minimize environmental impact. Building a gas pipeline through the Amazon required overcoming significant engineering obstacles, from navigating extensive water networks to addressing soil instability. The project's most difficult section, known as Segment B1, involved the installation of a 197-kilometer trunk line with 20-inch diameter pipes and over 70 kilometers of branch lines to supply gas to Coari, Codajas, and Anori. Given the remote nature of the construction sites, a unique logistical framework was developed. The Amazon River system, with seasonal water level variations of up to 14 meters, posed challenges for transporting materials and workers. The solution involved using 280 barges and over 500 pieces of heavy equipment, 5 modern helicopters, including the S-64 Skycrane, capable of carrying 8 tons, and the K-Max 4-ton capacity, used to transport 1,000 meters of pipeline daily. Bell 212 and Esquilo helicopters for personnel transport helicopters played a crucial role in expediting construction by airlifting pipes and workers to hard-to-reach areas, allowing work to continue regardless of river conditions. The pipeline crossed sensitive ecosystems, including flooded forests and major rivers such as the Solomos. To minimize environmental damage, innovative techniques were employed. Directional drilling. This method allowed pipeline installation beneath riverbeds without disturbing aquatic habitats. The Solomos River crossing was particularly challenging, requiring a 1,825-meter-long horizontal drilling operation at a depth of 115 meters. Barge-based construction. Specially designed floating platforms, bag barges, were equipped with welding and assembly stations, allowing pipe sections to be prepared and lowered into place with minimal ground disturbance. Reforestation and ecosystem restoration. Over 200,000 native trees were planted to compensate for vegetation cleared during construction. Seeds and seedlings were cultivated in project-run nurseries using specimens collected from the forest itself. Several pioneering construction methods were employed to adapt to the Amazon's challenging conditions. Pipeline installation in flooded areas. Floating barges, known as H-barges, were deployed ahead of construction zones, allowing 2 excavators, one for digging and another for stabilization, to work in tandem. Use of specialized cranes and pulleys. Mareka barges, equipped with cranes, facilitated the precise positioning and welding of pipeline sections, reducing manual labor risks and improving efficiency. Pipeline burial and stabilization. In swampy terrain, sections of the pipeline were weighted with concrete to prevent buoyancy, ensuring long-term stability. Remote monitoring and fiber optic integration. Alongside the gas pipeline, fiber optic cables were installed to facilitate real-time monitoring and communication between operational centers. Health, safety, and workforce management. At the peak of construction, more than 7,000 workers were employed, 70% of whom were local hires. Comprehensive training programs were implemented to ensure compliance with safety and quality standards, with the project receiving certifications such as ISO 9001, Quality Management, OSIS 18001, Occupational Safety, and ISO 14001, Environmental Management. To support the workforce in the remote rainforest, multiple temporary camps were established, offering climate-controlled accommodation, health and dental clinics, recreation areas, including sports facilities, and a small cinema dining halls with proper nutrition programs. Additionally, 16 boats and 7 floating accommodations were used for mobile work teams, reducing travel time and improving efficiency. Working in the Amazon posed health risks, including malaria and yellow fever. The project implemented daily vector control programs, including fumigation vaccination campaigns, on-site medical support, ensuring 0 cases of malaria or yellow fever were contracted within the project zone. Community engagement and social responsibility. Recognizing its impact on local communities, the consortium launched several social initiatives. Employment for disabled workers. 8 individuals with disabilities were hired to work in forestry nurseries. Educational support. A permanent library was donated to local schools. Sustainable agriculture projects. Training in pesticide-free vegetable farming was provided, boosting local food security. Cultural programs. Traveling libraries and mobile cinema events were organized for nearby villages. After construction, the pipeline underwent rigorous hydrostatic testing, where water was pumped through at high pressure to verify integrity. Internal inspection tools, known as pigs, were used to detect any deformations. Once verified, the pipeline was dried and prepared for operation. The Urucu-Coari-Manaus gas pipeline is now a key energy lifeline for the region, supplying cleaner, more affordable natural gas to industries and power plants across Amazonas. The project demonstrated that large-scale infrastructure can be developed responsibly within the Amazon, balancing economic progress with environmental stewardship. By employing cutting-edge engineering, sustainable practices, and strong community involvement, the Andrade Gutierrez-led consortium successfully delivered one of Brazil's most challenging energy projects, setting a benchmark for future developments in ecologically sensitive areas. Andrade Gutierrez TOM Project, Oriximiná-Manaus Transmission Line. The Andrade Gutierrez TOM Project is a large-scale infrastructure initiative focused on the construction of the Oriximiná-Manaus transmission line in Brazil. This project plays a crucial role in enhancing the country's electrical grid, improving energy distribution, and ensuring a more stable power supply to the northern regions, particularly the state of Amazonas. Given the challenging terrain and environmental considerations, the project requires extensive planning, logistics, and environmental management to ensure its successful execution. The Oriximiná-Manaus transmission line is a high-voltage power transmission corridor designed to connect Oriximiná, a municipality in the state of Pará, to Manaus, the capital of Amazonas. The project aims to strengthen energy security in the region by integrating isolated power grids into the national electricity system, reduce dependency on fossil fuels, particularly diesel-powered generators used in remote areas, support regional economic growth by providing a stable and reliable power supply, minimize environmental impact through responsible construction practices and ecological restoration programs. Challenges in construction. The project faces numerous natural, geographical, and hydrological challenges that influence the planning and execution of the work. The Amazon region is characterized by dense forests, large rivers, and difficult terrain, making transportation and installation complex. Key challenges include access to remote areas. Many parts of the project route are in isolated locations, requiring careful planning of logistics and resource distribution. Environmental sensitivity. The Amazon rainforest is one of the most biodiverse ecosystems in the world, necessitating strict environmental regulations to minimize deforestation and ecological disruption. Hydrological obstacles. The region experiences heavy rainfall and seasonal flooding, impacting construction timelines and requiring adaptive engineering solutions. As part of the construction, selective tree removal is necessary in the transmission line's right-of-way to prevent interference with power cables. The removal process follows strict environmental guidelines to ensure minimal impact on the surrounding ecosystem. Key measures include safe tree removal, Some trees are too tall and can become entangled with power lines. These trees are carefully felled in an open direction to avoid damaging the surrounding forest. Wood measurement and documentation. All timber removed from the construction area is measured, recorded, and accounted for to ensure sustainable management of forest resources. Reforestation and land restoration. After the construction of the towers and access routes, degraded areas undergo ecological restoration to maintain environmental balance. Economic and social impact beyond improving energy infrastructure. The Andrade Gutierrez TOM project contributes to the local economy by creating employment opportunities and boosting regional development. The project provides jobs for engineers, construction workers, environmental specialists, and logistics experts, many of whom are recruited locally. Additionally, it stimulates growth by enhancing power reliability for businesses and households, encouraging industrial investments in the region.